Thank you. Okay, great. Well, good to see everyone here this morning. I'm excited to be able to present this recent work with Tim Randolph, who is a computer science PhD student here at Columbia. So today I'm going to be talking about one-sided allocation, right? So this is basically where we're giving away a set of objects. And usually we think of these objects or items as being heterogeneous in various ways. And we have agents who are going to each receive at most one item, but they have heterogeneous values for these items. So they don't necessarily, they care which item they get, and they don't necessarily agree on which item is best. Now, there are many settings that fit this, three kind of important ones that should be familiar to everyone in this audience, thinking about giving away public school seats, thinking about affordable housing allocation, or organs. You know, you only want one organ if you're in need, but and they're for various biological reasons, you might be compatible with certain organs and not others. Okay, now in theory, there's a really nice solution to this problem, right? And so that's basically fake money, right? Create a virtual market, give everyone, say, 1 unit of virtual currency, and then let them use that to purchase probability shares. And so this is called competitive equilibrium from equal incomes, or CEEI. And it has a couple of desirable properties. One, it's fair in the sense that nobody envies anyone else's ex-ante assignment. And second, it's efficient, right? It's Pareto efficient. So if this were the matching in theory workshop, we'd just spend all of our time talking about competitive equilibrium from equal incomes. But as far as I know, basically nowhere actually uses this mechanism for a variety of reasons. Some of you may be familiar with Eric Budish's work on course match. That's the one quasi-exception that I know to this, although even there they've had to deviate to basically account for creating a reasonable preference reporting language. So basically, this is not a very practical solution, or at least appears not to be. So the question is, are there practical alternatives? And I don't want to get into a long debate about defining the term practical, but one kind of easy definition to use is that a mechanism is practical if it's actually used in practice. So today I'm going to tell you a little bit about a mechanism that's being used to allocate hunting permits in Alaska. Right, so here's the state of Alaska, for those of you who aren't familiar. It's massive. It has a lot of wildlife. People go there for various reasons to appreciate the wildlife, but hunting is also a big part of life there. Right? And so every year, the state doesn't just want to let everyone go willy-nilly. There's a limited number of permits. So a limited number of, say, moose or bear that can be shot in a given year. The allocation of these permits is conducted once per year. And actually, there's separate allocations for each species. So if you want to get a moose permit, there's an application process for that. If you want to get a permit for hunting bears, there's a separate application process for that. But within each species, you can only get one permit. And you might say, okay, well, now that we've limited it to just permits for hunting moose, are there really heterogeneous items? You know, like, do I care which permit I get? And it turns out the answer is yes. So there's a lot of information specified on your permit. So not only does it say what species you're hunting, but also what gender you're hunting, because it turns out that hunting females versus males has very different implications on the population dynamics and reproduction of these species. And so the ecologists that are setting the quotas may set different quotas for females versus males. Second, the permit specifies where in the state you can hunt. Right? So it wouldn't be any good to determine statewide we can lose this many moose, but then everyone goes and shoots all the moose close to the major metropolitan areas and leaves others unhunted. And so where to hunt? There's when to hunt. So there's certain seasons that you're restricted, and in some cases even how. So like, are you hunting with bow and arrow? Are you hunting with a shotgun? Are you hunting with a trap? So all of these different parameters mean that people are going to have heterogeneous preferences over the various permits that are being allocated. So the plan for today, I'm going to tell you about a parallel lottery mechanism that they're actually using currently to allocate these permits. I'm going to conduct a theoretical analysis of this mechanism. And I'm going to kind of make 3 arguments in favor of this mechanism, basically saying why I think the mechanism itself is a pretty reasonable way of resolving preferences. And then finally, I'm going to say, well, okay, suppose you don't care at all about hunting. In fact, maybe even you think you have moral problems with hunting, right? The mechanism itself is still interesting. And the question is, when and where might it be useful? And so I'll kind of close the talk by giving a few perspectives on that question. Okay, so what's the mechanism that they're using? So let's suppose we have 4 permit types, right? These are differentiated along the dimensions that we just described. And we have multiple copies of each permit. So for example, we have 2 copies of permit A, 2 copies of permit B, and 4 copies each of permits C and D. Okay. How are we going to allocate these items? Well, we're going to have separate lotteries for each type of permits. Okay, and so I want you to think of this image I have as being literally like a bucket of where we're going to put lottery tickets. So we basically give each applicant 6 lottery tickets that they can spend, and they can allocate the 6 tickets however they want among these buckets. So importantly, hunters can apply multiple times for any given permit. So if you wanted, you could put all 6 of your tickets in the bucket for permit A. By doing so, you have an advantage. You're more likely to actually win this permit than if you'd only put 1 or 2 tickets in there. Now, if you know that A is very popular, then you might say, well, I should also hedge my bets and put a couple of tickets in bucket C, which is less popular. I'm more likely to win. Right? And so here's an example strategy that you might use. It consists of 2 components. One, a number of tickets in each bucket, and second, a ranking of all of the items that you've applied for. Okay. Now, how is this ranking going to be used? Well, once hunters have allocated their tickets, we're going to have separate lotteries for each item. Right? But there's a slight twist, because remember, hunters can only win at most 1 permit overall. So what if my name is drawn for both permits A and C? That's where the ranking that I gave is going to come into play. I said that I preferred A to C. So in that case, I will keep permit A, and they're going to draw a new name for permit C. And this process is going to repeat until basically all of the permits have been allocated.
Nick, can I say something?
Absolutely.
This is Utku. So this is very similar to like raffles, right? At county fairs, etc. Just, I guess the difference is you can win multiple objects. Sometimes it depends on the rules of the raffle. Right. Yeah,
that's exactly right. So that, I would say, is further evidence that this sort of mechanism appears to be fairly practical and plausible. And I agree with you. The only real difference between the standard raffle at a county fair and this one is the fact that you have unit demand agents, so you're only allowed to win 1 item. And so actually another way of describing or thinking about this mechanism is the following. Each ticket gets a lottery number that's, say, uniformly distributed from 0 to 1. Then your priority for each item is going to be the best lottery number among the tickets that you spent on it. So that's how, so we can use basically where you placed items to determine a priority ranking for each item. And then actually the second stage, the clearing procedure, can exactly be thought of as item proposing deferred acceptance with these new priorities. So you can kind of think of this as a sort of deferred acceptance procedure, except in the first stage, you get to influence where you get higher or lower priority based on where you put your tickets. Any other questions about how this mechanism works? Because there's no point in going on if the mechanism itself doesn't make sense.
Nick, I think that it's very clear how mechanism works, and I think, as Utku mentioned, many of us probably saw it if you go to the school or played some raffles. But it's also evident that it has some strategic manipulability issues and efficiency, right?
So say a little bit more about strategic manipulability.
Okay, go ahead. Sure.
No, I'm curious. What are you thinking of?
So it depends on my strategy. Definitely depends on the strategies of others, and on my and how I perceive whether others where they put their tickets, and of course others also depends optimal strategy how they think I will where I put tickets.
Right.
So you have a parallel with the deferred acceptance, but definitely this parallel after you submit preferences, right? So there is a huge can be a lot of efficiency loss.
Totally, right. Yeah, so algorithmically it has this parallel to deferred acceptance, but unlike deferred acceptance, there's not going to be a dominant strategy in this mechanism. So exactly as you said, one concern we're going to have is that in order to figure out where I should put my tickets, I need to have some sense of which are the most competitive and the least competitive items. And I'll formalize exactly what information I'm going to assume agents have in a minute. And at the end, I'm going to spend a little bit of time saying, is it realistic to think that they might have this information? Because that will be a practical concern for sure. Yeah. So, okay, so what's the individual decision problem? Well, we have a finite set of types of items. Each agent has a vector of values saying how much they value receiving each item. Okay. Now, they're going to choose these two components that we mentioned, the number of tickets and the ranking of the items, number of tickets in each lottery. And they're going to react exactly as was just pointed out, they're going to react to perceived win probabilities for each item. So we're going to assume that each item has some known win probability, PI. Implicitly, this is arising endogenously from the behavior of the other agents. Right? But in terms of solving for my best response, I just need to know the PIs, which is telling me kind of for a single ticket placed in lottery I, how likely is it to be drawn? Okay. Now from this allows us to define basically what's going to happen for any given strategy you might choose. Okay. Now that definition looks a little bit messy at first, but it's really not too bad, right? Basically it's saying your chance of winning item I, given your strategy. Well, two things have to happen. First of all, one of your tickets that you placed in item I needs to be drawn. That's the first green component. And then the second component says, also, any tickets that you placed for items that are preferred to item I should not be drawn. Okay, and then your goal is to choose your strategy to maximize your expected payout. Okay, now, even if you know the probabilities P, this seems like a highly non-trivial optimization problem. So let's just give ourselves a little bit of practice, right? So suppose we have this example. So we have two items, A and B, and say your value for A is 10, your value for B is 5, and these are the win probabilities that you anticipate. So if you only have one ticket, where do you want to spend that ticket? Anyone want to volunteer? Go ahead. People are too shy? Two? I see a few. B. Yeah, okay, great. So item B is indeed correct. Basically, we can just do an expected value calculation, right? 2/3 times 5 is bigger than 1/4 times 10. So you would want to put your ticket in item B. Now, what if we had two tickets? So one natural guess might be if the first ticket should go in item B, then the second ticket should also go for item B. That turns out not to be the case, right? And it's easiest to see if you imagine the item B actually had 100% win probability, then there's really no point in putting a second ticket for item B. But even with a high win probability like 2/3, you'd actually rather, it turns out you'd rather split your tickets between A and B. So you want to put one ticket in item A and one ticket in item B if you have two tickets. And that will get you an expected payout of 5. So with two tickets and 2 items, maybe it's not so hard to just kind of enumerate over all the possible ways you could use the tickets and calculate the optimal strategy. But in general, we want a solution. Thankfully, that's already been solved. It turns out a sequentially greedy strategy is optimal. So basically, you can ask yourself, if I only had one ticket, what's the best place to put it? And then for the second ticket, say, well, given that I know I'm going to put one ticket in for item B, where should I put my second ticket to maximize its incremental value? And that sort of greedy strategy turns out to be optimal.
Nick, here Tomas with a question, but the MIA, margin improvement algorithm, I think it requires independence on admission probabilities, right?
Right.
To be optimal. And another question that I had is related to this too, is it possible also to approximate this problem by like cloning each of the objects in the number of total tickets and then like applying like to each of them? Have you thought about that?
Yeah, so actually you're exactly right? So this strategy is optimal if the win probabilities are independent. In a finite market, that's not necessarily going to be the case. I should have probably clarified, in our analysis, we're working in the continuum limit that you suggest. So basically, you can think of this as being a large number of permits for each type of item. And so each agent's kind of effect on the market is going to be negligible. And in that limit, the win probabilities are indeed independent across tickets.
Okay, great, thanks.
So Nick, if you put 2 tickets, your probability is still 2/3 for each ticket. Is that what that means for B?
Exactly. So therefore, if you put 2 tickets for B, your probability that neither is drawn would be 1/3 squared, or 1/9. So your overall probability of receiving B would be 8/9. Yeah, that's right. Okay. And so this was just the optimization problem for a single agent. Of course, we need to define an equilibrium. I'm not going to spend too much time on it, but basically these probabilities PI should clear the market. So basically when everyone's best responding to these perceived probabilities PI, we need it to be the case that we don't over allocate any item. And any item that we have left over at the end that isn't fully claimed should have a win probability of 1. And it turns out that there always exists a K-ticket equilibrium. In general, it's not unique, although if K is 1, it is unique. Okay, so now the theory I want to present is basically what can we say about these equilibria? Are they any good? So the first result in the paper is basically if we have very little supply relative to demand, then the outcomes from this mechanism approximate a competitive equilibrium from equal incomes, in the sense that for every agent, the ratio of their utilities in the 2 mechanisms is close to 1. Right. I just mentioned the equilibrium may not be unique, but this theorem holds for any equilibrium you choose. And so the intuition here, I think, is basically just that we can think of the tickets as being a sort of virtual currency. So perhaps it's not so surprising that this parallel lottery mechanism can be thought of as a form of virtual currency. And this applies, for example, here's some data from bison hunts in the state of Alaska, where they're giving, between 20 and 60 permits, but there's many, many more applications than that. So your chance of winning is vanishingly small. And I would say this kind of suggests that in this case, the outcome should be similar to a competitive equilibrium.
Sorry, Nick, for interrupting, but can you be more precise? So you mentioned there are many equilibrium parallel lottery. So which kind of equilibrium you consider? And does it mean that it's also efficient?
Yeah, so it does mean that it's approximately efficient. I mean, kind of within the epsilons of error. And this statement holds for any equilibrium. So pick pick whichever equilibrium you want, and for each agent, they're going to get utility approximately equal to their utility in competitive equilibrium from equal incomes.
And one more question, sorry. And supply goes to zero. What does it mean? Can you be more specific?
Yeah, so we have basically really, you can think of there being supply and demand. And really, what I want is that the ratio of supply to demand goes to zero. So either supply goes to zero or the number of agents increases, holding fixed the relative quantities of each good. So maybe I know I have twice as much of good one as good two, but I'm letting the ratio of goods to agents go to zero. Okay, so that was useful for bison, but it turns out that for other species, there's a wide range of win probabilities. So here for moose, we see for some permits, it's a 2% chance of winning.
Could I ask a question?
Sure.
Sorry, Bobby here. So just about that case, not to give you too much of a hard time, but why do we care about the benchmark where the ratio of goods to people goes to zero? I mean, don't we just throw our hands up and say, no one should hunt in that case, basically?
Well, so first of all, whether I believe that in the case of hunting, I think is a separate question, but there's a lot of social goods settings where supply is far less than demand. So for example, affordable housing is one area that I've spent a lot of time thinking about, where often there are 1,000 applicants for each spot. And sure, you could throw your hands up and say, well, we don't really care how we allocate this affordable housing. But I think they're really, the people who are trying to get it really do care. So knowing that you're allocating the limited supply well, I think makes sense.
I hate to say it, but Nick has only 1 minute. So
wow.
Please,
okay.
Please use it.
Well, we're gonna blast through this. So basically, there's two types of inefficiency in general, right? So these outcomes are not going to be perfectly efficient. One is this nonlinearity in tickets that causes you to want to kind of split your tickets across multiple items. Second is the fact that tickets are indivisible. And what that means is that there might be items left over at the end where no one applied for those items, but they didn't apply for them not because they wouldn't have wanted them, but just because there was an opportunity cost. If I only have one ticket, I'm going to spend it on whatever maximizes my bang for buck, which may mean that in some cases, I'll spend it on a competitive allocation, I'll lose that ticket, and then I'll wish, I wish I could claim one of the leftover items. Okay, so since I don't really have any time, all I'm going to do is say, in the paper, we basically quantify both of these. We give examples of how they can lead to inefficiency, but we also bound how inefficient it can be. Right? And one thing to note is that we get fairly tight bounds on how inefficient this can be, and well-known mechanisms like random serial dictatorship, actually, according to this definition of inefficiency, can be arbitrarily inefficient. And that's a result proved by a team at Microsoft Research several years ago. So kind of it's not trivial to get good approximation results. Okay. So in some sense, I would view this second set of results as saying, well, even if supply is not so small, there's kind of bounded inefficiency from using this mechanism. Now, the final point I want to make is that actually we argue that in some cases, the parallel lottery can actually lead to outcomes that are better than CEEI. And basically the reason is, let's take this example. We have one copy of each item. Everyone agrees that hunting close to home is preferable to going to some very remote region of the state. But some people can reach the remote region by like a private chartered plane, and other people can't. And so if we use CEEI or any other non-wasteful mechanism, we're going to end up basically flipping a coin to decide who ends up getting the more desirable permit close to Anchorage. Whereas if we use a two-ticket lottery, the person who doesn't value the remote permit at all is going to spend all of their tickets trying to get the more popular item. Whereas the person who has an outside option and is willing to go to the remote region might spend one of their tickets ensuring that they get to the remote region. And as a result, actually poor Paul, who maybe doesn't have the money to fly elsewhere, has a higher chance of getting the local permit. And so that arguably is a more efficient allocation and certainly results in a better allocation for Paul, because now he has a 2/3 chance of getting it rather than 1/2 chance. And so I think this last point is more general than this specific mechanism. It's really about understanding when can the threat of wasting items basically result in better outcomes for people with stronger preferences for popular items.
Okay.
I know I need to wrap up. Basically, we formalize this idea that fewer tickets results in better outcomes for people with strong preferences. And basically what this means is the theory says this mechanism should work well, but we want to know, could it be used in other settings? And in fact, it is used to allocate housing in Singapore. So Singapore, 80% of the population lives in government-built housing, and all of that housing is allocated using a one-ticket lottery. There are really key challenges to overcome. So one is, I would say the biggest is, how do we let applicants know PI? There's a variety of ways to do it. Alaska publishes last year's data. I would say that's not perfect. Singapore goes a step further and actually publishes real-time data of, based on what everyone else is doing, what is your chance of winning each item? And you can kind of react to that for a period of time up to the application deadline. Second concern is, do we want to favor agents with strong preferences? And we argue in the paper that there are cases where you actually don't. So we argue, for example, that school choice is one example where we don't necessarily want to have a wasteful mechanism that favors agents with strong preferences. So to close, I think this is a practical mechanism. We've kind of conducted a fairly thorough theoretical analysis. Unfortunately, I didn't get to kind of go through all the details, but it's all available on the paper on my website. We do think there are important caveats to applying this in practice. And actually in the paper, we talk about settings where we'd recommend, for example, something simpler like a random serial dictatorship, rather than something that relies on people knowing how competitive items are. But we also think that this could be useful for other contexts, namely affordable housing in the United States, which generally features mechanisms that give applicants very little choice over what they're going to get. And we think that this could be a practical way to give people more choice. So thanks. I know I went over time.
Yes.
I'll close there.
So this is the toughest task to, to stop you, or at least to make it possible. But especially it is difficult online, and especially it is difficult if the paper is actually, personally very interesting to me. So we have a 10-minute break now. Let's go back to the lobby and chat, and then come back for our roundtable. See you soon.